Hello and welcome back to Data-Driven Methods in Dynamical Systems. Today, I want to tell you why I reject 90% of the papers that I run into coming from the engineering fields. And it's a very, very simple problem, and it's a very common assumption. And in fact, you might have made this assumption already. But before I can tell you what's in here, I need to explain to you what reproducing kernel Hilbert spaces are.
Because I know who killed him. This is who.
And so for now, in order to get to the point, I'm going to talk to you about reproducing kernel Hilbert spaces. Now, we've actually seen kernel functions come up several times in this class. We saw them show up for making covariance matrices in kriging or doing kernel PCA. We saw them show up as a sum of features when we did the amplitude modulation section. So there we used a kernel function to not only project a field of amplitude modulated signals down to just a single one, but we also saw how we can use the kernel function to reproduce the values that come out of the amplitude modulation. Then we had to do a little bit of filtering, and then we got our signal back. And from these, you might get the sense that maybe kernel functions appear sort of sporadically throughout data science. But I'm going to tell you that kernel functions are the very core of data science. And most engineers don't really even realize this. When you take a look at the Nyquist theorem, there's actually an underlying reproducing kernel Hilbert space for which that whole theorem actually works on. And this Hilbert space is called the Paley Wiener Space. So let's talk about the general definition of what a kernel space is. So a reproducing kernel Hilbert space is a Hilbert space of functions that map, say, a set X, could be a subset of Rn, could be complex plane, or many other things. And so what we're going to do is we're going to take a look at a Hilbert space from the set X to, say, the reals or the complex numbers. And so the core thing that makes a reproducing kernel Hilbert space a reproducing kernel Hilbert space is that we have function evaluation being a bounded functional. So what this means is that if I take a function f and I map it to f of x for some fixed x, then that should be a bounded linear functional on the Hilbert space. There's a thing called the Reese theorem that basically says that whenever you have a bounded linear functional, there is going to be a unique element inside your Hilbert space that reproduces that functional through the inner product. And in particular, we're reproducing the function evaluation. That's where they get their name, as reproducing kernels. So we'll have so for the evaluation functional at a point x, we have the reproducing kernel centered at x inside of our Hilbert space. And you can make something called the kernel function, which is a positive definite kernel, which has its own sort of definition. And we make this by saying that kxy, for 2 points x and y inside of x, we define it as being the inner product with ky with kx in our Hilbert space. Now, the order does matter there if you're working with a complex valued function, because then the inner product itself is going to end up being complex valued, and so is the kernel. If we're working over a space just maps into the reals, then we don't have to worry about that so much. You can have kx and then ky, but just out of good habit, you should always put ky first. And so this kxy is called the kernel function for the Hilbert space. And there's something called the Ehrenstein-Mohr theorem that says anytime you have a kernel function that has a positive definite kernel, there exists a unique Hilbert space corresponding to that. What does it mean to be a positive definite kernel? Well, it means that if you take a finite collection of points in your set X and you make this gram matrix that we did with all of our covariances, then that should be positive semi-definite. As long as that's positive semi-definite, there is going to be a Hilbert space that corresponds to this positive definite kernel, and that's our reproduced kernel Hilbert space. Okay, so I said kernel functions everywhere. This seems kind of abstract. And I mean, Gaussian RBF kernels were really pushed forward by Vapnik back in the early 1990s and Shulkov. And that comes up in, say, support vector machines. And then we have all these like RBF kernels and all those things, and that all seems rather modern. And so to a typical engineer who's never heard of reproducing kernels all through their undergrad or even their grad school, and they go on and they try to do some research in this field, and they bump into these things that seem to have come from these things like Gaussian processes, it seems very, very abstract and maybe very niche as far as their applications. But the truth is, reproducing kernels have been in the literature and used throughout mathematics and engineering for the past century. I think they got their inception as a proper study of themselves well before Ehrenstein came along and codified everything in his 1950 paper. And even something that mathematicians and engineers study through undergraduate and graduate school are Green's functions, and these are kernels in a certain sense. Kernel functions take the place of the delta function, where the delta function really represents the function evaluation in things like the Schwartz space, where we had tempered distributions. Now, since kernel functions have to be inside the Hilbert space, that means that they have to be proper functions themselves. And so standing in for these delta functions are these kernel functions. And in particular, we have to be working over function spaces.
I said I would name the individual responsible for this murder, and that is what I'm doing.
Now, what is this reason why I reject all those papers that I put in the secret envelope here? Well, actually, I didn't write anything inside the envelope. I just write reject on it. But the truth is, most engineers think that L2 is a function space, and it is not. So L2 on the surface looks like it might be a function space. People write the norm of L2 as being the integral from, say, negative infinity to infinity, or 0 to 1 of the absolute value of f of x squared dx. Now, while that is a function that we're putting inside of that integral, that is actually a representative of an equivalence class, which is the actual elements inside of our L2 space. L2 consists of equivalence classes of functions. And what this means is that we have some special way of defining equality of elements inside of L2. So if we take an equivalence class out of L2, one of the members of L2, and we take two elements out of that equivalence class, those are going to be two different functions that could actually differ on a set of measure 0. So if we have any, say, finite point set, that's a big measure 0 set, and the difference between these two functions are going to be 0, except possibly on those measure 0 sets. And when it comes to sampling problems, if you take a finite number of elements and you try to look to L2 to sort of interpolate those elements or treat those as samples of one of your elements in L2, it doesn't mean anything, because any sample set is measure 0, and elements in L2 can do anything they want around these sampled points. And so in that sense, function evaluation is meaningless for L2, and that means it can't be a reproducing kernel Hilbert space. But then you might argue with me, well, what is all this sampling theory? I mean, we have the Nyquist theorem, and that seems to be working over L2 functions. And I'm going to tell you right now, the Nyquist theorem has nothing to do with L2. Okay, it has something to do with L2, but the functions itself that you're sampling are not from just L2. They're actually from what we call the Paley Wiener space. Okay, so there are a few things that we need to know about the Fourier transform and functions that satisfy the L2 norm. So the fundamental thing we're going to be talking about here is that the Fourier transform of an L2 function gives you another function that satisfies the L2 norm. And so if you have a function whose L2 norm is finite, then the Fourier transform of that has an L2 norm that is also finite. And that's a very important step to start with. The Paley Wiener theorem says that if you start with a function that is non-zero only on a compact subset of frequency domain, and you take the inverse Fourier transform, then the result is going to be a function that is entire. And this is a very easy thing to show, and it basically uses the dominated convergence theorem to move differentiation in through the integral, and then you can show that it satisfies Cauchy-Riemann equations, and you can show that it works for every single z that you choose in the complex plane. Again, you might be railing against me and saying, well, this doesn't sound like we're talking about sampling theorem in the complex plane. This isn't the real line. At any complex entire function, we can restrict to just the complex plane, and we can talk about only the real values, and so we can turn this into statements about real entire functions, things that are really common to you, like sines and cosines and exponential functions. What I'm going to do then is I'm going to restrict our focus to just being a single interval, say -a to a, inside of our frequency domain. And we're going to take a look at all functions that are non-zero only inside of that region. And so if I take the Fourier transform from -infinity to infinity, well, really we can chop off those two tails and just look at it as an integral from -a to a. And then we're looking for the inverse Fourier transform of this. And so we're basically going to have, say, f hat of omega times e to the I x times omega. And this is going to give us what we'll call f of x, or you can change x for z if you prefer, and this is going to be our entire function. So we want to make a reproducing kernel Hilbert space. What we're going to do is we're going to take these entire functions that satisfy the L2 norm, and what we're going to do is we're going to take their Fourier transform, which we know is compactly supported in a certain region of the frequency domain, -a to a. Now what this gives us is a way to define the inner product. We're not going to define the inner product on the functions themselves. We're going to define the inner product on their Fourier transforms. So we'll say that the inner product between two of these functions out of our Paley Wiener space, say f and g, this inner product is defined as being the L2 inner product between f hat and g hat on negative a to a. So this gives us a well-defined inner product, and it gives us a well-defined Hilbert space. Now, here's where the cool thing is. We can make the reproducing kernel for the Paley Wiener space really easy, and just using the theory of Fourier transforms. So remember, this function that we are trying to use to make the reproducing kernel Hilbert space is going to be inside of our Paley Wiener space itself. So that means it has to live within this negative a to a region inside of our frequency domain. But so does every other function inside that space. We know that we can recover function evaluation using the inverse Fourier transform here. Okay, so let's take a function f of x, and we want to evaluate it at a point y in our Paley Wiener space. The Paley Wiener space has well-defined function evaluation at the very least, because it is a space of entire functions. So I want to know, what is function evaluation at the point y? What does that look like from the kernel space perspective? And so we're trying to find a kernel function centered at y. So the route that we're going to do is that we're going to figure out what its Fourier transform is, and that's because the inner product for Paley Wiener functions happens in the frequency domain. So what I'm going to do is I'm going to take a look at the only thing that can really work here, and that is the inverse Fourier transform. So we're trying to figure out what is f of y, and well, that is going to be the integral from negative infinity to infinity of f hat of omega times e to the I y times omega dy. But since we know that f hat of omega is compactly supported, we can change this whole integral down to negative a to a, and that looks a lot like our inner product. So how do we dress this up to be exactly our inner product, which would tell us what the Fourier transform is of our reproducing kernel? So we have f hat of w, or f hat of omega, and we know that that's half of our inner product. So everything else has to correspond to our reproducing kernel. So what we're going to do is we need to put that under a bar, because we know that the other half of the inner product has to be conjugated. So then we make this adjustment, and so what we get is we flip the sign and the exponential, we put a bar on top, and so we get e to the minus I y omega bar. But what you're missing there then is that e to the minus I y omega is not compactly supported, so it can't be inside of our Paley Wiener space. So how do we fix this? Well, we're going to make a change here that isn't going to change anything else about our inner product, and that is we're going to multiply by the characteristic function of negative a to a. And what happens when we do that is we end up getting the Fourier transform of whatever our reproducing kernel is. And we know this is fine because, I mean, multiplying by this characteristic function isn't going to change anything, because the compactly supportedness of our Fourier transform of f already restricted our interval to negative a to a. So nothing bad happens just by multiplying by this characteristic function, which is just 1 inside of negative a to a. So then we have the Fourier transform of our reproducing kernel centered at y. And that this is a function of omega for a fixed y, and we want to figure out what this function is as a function of x. And so we're going to use the inverse Fourier transform on this, evaluate that on x, and what this ends up giving you is the sinc function, and it's going to be twice the sinc function. It's like 2 times sine of a times x minus y bar divided by a times x minus y bar. There might be 2 pi factors floating around in there, and I'll fix that in the edits, and you'll see those on the screen here. But that shows us that this Paley Wiener space is a reproducing kernel Hilbert space. Now, how do we get the Nyquist theorem out of this? And how do we do sampling out of this? And that is the next step. So this next bit is always a little tricky for me. I do most of these videos sort of off the cuff. I just sit in front of a camera and start jabbering. And I have a vague idea of what I want to say, and then I say about a million things. I edit it down to about 20 minutes, 30 minutes. And so some of my constants might be off, some of my scalings might be off, and I'll adjust it when I actually write all the equations. But the fundamental idea of the Nyquist theorem and how it comes into the sampling theory and the Paley Wiener space is that when you take a look at these band limited functions, which is what the Paley Wiener space is, just we fixed this interval negative a to a. When you fix these band limited functions, you take a look at their inner product, which is coming from the L2 inner product on Fourier transforms. The collection of functions e to the I n omega are orthogonal in minus a to a, or, times some sort of frequency that depends on a. And what's really cool is that we already know that these functions themselves correspond to our reproducing kernels. And so if we just multiply by the characteristic function of negative a to a, then we have a countable number of kernels, And we know that they must span the space because the norm on the Paley Wiener space comes from this L2 space, and these exponential functions are a complete basis on this L2 space. So, ta-da, we have sampling theory. If you take a function and you expand it in terms of this orthonormal basis, then you get kernel functions. And it's a very unique set of kernel functions that are actually pairwise orthogonal. It is a book! What we have is a collection of shifted sinc functions, and they're all pairwise orthogonal according to this L2 inner product that we came up with in the Fourier domain. We can go ahead and we can decompose any function we want using the sinc functions, which are now an orthonormal basis, and ta-da, that is your sampling theorem. You'll notice that where we sampled these functions depended on the choice of frequency that was necessary to make this an orthonormal basis in the L2 space, and then that's feeding directly into where we're sampling this function. And so we see that we sample this function at the appropriate frequency, and then we can get exact reproduction. And that's the Nyquist theorem. And one last thing I should mention is that we are actually getting bounded point evaluation. And we can see that through the Cauchy-Schwarz inequality. Essentially, if we take a function f and take the inner product with one of these kernel functions that we made up, then evaluation of a function at a point y in absolute values is equal to this inner product of f with this kernel function centered at y. And then we can just use the Cauchy-Schwarz inequality, and then we get this boundedness property for the functional. So then we have the norm of f times the norm of this kernel function. And now my child is running away. So then you see, after using the Cauchy-Schwarz inequality, that you have the norm of f times the norm of our kernel function centered at y. That kernel function y becomes the constant that gives us the boundedness of our functional. So sampling theory is really where all of data science starts. You need to be able to sample functions, and the Nyquist theorem is pretty much as old as any sort of sampling theorem goes. And you can see it's directly connected to a proper function space and not just an L2 space. We not only have proven the Nyquist theorem, but we now have a solid reproducing kernel Hilbert space to start with for all of our discussions. And so we're going to talk about other kernel spaces, and they're going to be essential for any time we want to do data science. There's no data science without samples, and you can't have samples without function spaces. And almost every Hilbert function space is actually a reproducing kernel Hilbert space in one form or another. Okay. So I think this is a really good point to stop. I have given you the Paley Wiener theorem. I have told you what the Paley Wiener space is, and we used the L2 norm on the Fourier transforms of these functions in order to give it a norm and an inner product. And we saw that that gave us a reproducing kernel that is actually pairwise orthogonal as long as you space out the centers just enough. And that gives us an orthonormal basis that we then used in order to get the Nyquist theorem. And so my children are starting to make a lot of noise out there, and obviously we had a visitor. And so I think it's going to be time for me to stop this. Anyway, thank you for watching, and next time we're going to dive into some operators over kernel spaces and talk about multiplication operators. All right, so with that, I'm checking out, and I'll see you next time.